Hi, in this lecture we will see the closure properties of finite languages. So now what we have set of finite languages, and for that set we want to see the closure properties. First of all, what is the definition of finite language? The definition is very simple, and you already know what is this finite language. Finite language means basically number of strings that is finite. So if you have a language, for example, consider this language A B and A B. If you consider this language L, then this is a finite language because there are only 4 strings. So we can say the language L is finite. So that is the one definition, means number of strings is finite. So this is the first definition. But this in the exam they can give you some other definition of finite language, because we can define this finite language in some other way. For example, they can give you this definition. Consider this definition. They can say that we have a language L such that there exists a natural number n, means there exists a natural number n such that there is a bijection between L and this set. So basically consider this set. We can say that there is a bijection between L and this set 1, 2 and so on n. So this is the definition. Now this is the definition of a finite language. This is another definition they can give you, means you have a language L and they can say that there exists a natural number such that there is a bijection between L and this set. Of course, in this definition they can say that because from this definition you can notice that L cannot be empty. So we can also say that okay, either L is this or L is empty. So now this is the complete definition of finite language. So actually this is just another way of defining finite language, nothing more. Okay, because this is a very simple definition. Number of strings is finite. This is a very simple definition. But in this definition, this is more sophisticated definition. In this definition, he is saying that we have a language L. For that language, there exists a natural number such that between L and between this set, means from 1 to that natural number n, between this set and this L, we have a 1-to-1 correspondence, or you can say we have a bijection. This symbol we are using for bijection. There exists a bijection between L and this set, or L is empty. Now this is the definition of, in that case we can say that L is finite language, because clearly you can say, for example, if your language L is AB. Now consider this language L. Now for this language L, there exists a natural number, and what is that natural number? That natural number is 3, because you can see that this language L has bijection with this set. Okay, that natural number that will exist is 3. You can see there exists a bijection between this L and this set. So this is another definition of finite language. Now we can also define finite languages in some other way. Remember why I am telling you all these different definitions of finite languages, because in exam they can give you any of these definitions, and some students, what they do, they cannot understand these definitions. Like if in the exam, if they explicitly give you that language is finite, then some student will understand. If they say that number of strings is finite, then also they can understand. But in the exam, if they give you this definition, that we have a natural number such that L and this set has a 1-to-1 correspondence, this definition cannot be understood by many students. So that is why I am telling you all these definitions. Now consider fourth definition of finite languages. This definition basically says that there exists a natural number n such that you can say that such that all strings belonging to L have length less than or equal to n. So this is also a definition of finite language. In that case we can say that L is finite. Okay, so try to understand this definition. Okay, let's take example and let's try to understand. So in this definition, consider this language L, A, and consider AB. Now consider this language L. So for this language What he's saying that L is finite if and only if there exists a natural number, such that for all strings of L, length of string is less than or equal to n. Basically, the length of every string in L is less than or equal to n. So this language L is finite. Why? Because you can say that there exists a natural number, and that natural number you can take 6. Okay, this natural number you can take, because you can see every string has length less than or equal to 6. So that is why you can say that this language L is this language L is finite language. So this is another definition of finite languages. Okay, and any of these definitions can be given to you in the exam. So consider this is another sophisticated definition. He's saying a language L is called finite language if there exists a natural number such that every string of L has length less than or equal to k. So this is the definition of finite language we have already seen. Now let's see the closure properties of finite languages. So what is the meaning of closure properties? Okay, closure property means basically you have a set. Let's assume this is your set A, and in this set you have some elements, and on these elements what we do, we define some operation. So basically on the elements of this set, let's take 2 elements from this set and let's define some operation on these elements. Now closure property says that this set A is closed under this operation. So for closure property, what 2 things we need? For closure property, 2 things that we need is a set and operation. Okay, we need a set, we need an operation, and we say that this set is closed under this operation if and only if you apply this operation on any elements of this set, then the result means this A star B, this result should also belong to this set. Then in that case we will say that this set is closed under this operation. Okay, for example, we know that set of regular languages are closed under union operation. So what it means? It means this: you have set of regular languages, so all the regular languages are here, L1, L2, L3 and so on. All the regular languages are present here. Okay, now when we say that set of regular languages are closed under a union operation, what it means? It means that if you take any 2 regular languages, if you take any 2 elements from this set, and in this set we have regular languages, so if you take any 2 regular languages, you apply the union, this result must belong to this set. And if this result belongs to this set, means this result means L1 union L2 is regular. So that's why we say that set of regular languages are closed under union operation. Now let's see the closure properties of finite languages. When we say that finite languages, then what we mean? We mean that all the finite languages are here. Okay, L1, L2, L3, all the finite languages are here. For example, this L1 can be empty language. For example, this L2 can be this. For example, this L3 can be A, B. Okay, for example, this L4 can be A, B, A, and so on. So all the finite languages are here. Every element in this set is a finite language. Remember, every element is a finite language. Okay, so now first we will see union. So set of finite languages is closed under union. Yes, because if you take a finite language, take any finite language, union with any other finite language, then this result means this union, this also will be finite language. If this is finite, then that union will also be finite. So we can say that set of finite languages is closed under union operation. Similarly, you can say intersection. Let's say intersection operation. If you have a finite set and if you have another finite language, so if you have a finite language, another finite language, if you take their intersection, then what will happen? Intersection of 2 finite languages will also be a finite language. So that's why you can say the result is also a finite language. So I can say that basically if you take L1, if you take L2 and you take their intersection, then this result will also be a finite language. Hence you can say that intersection of 2 finite languages is always a finite language. So set of finite languages is closed under intersection operation. Now let's see some other operations also you can see. For example, concatenation. For example, concatenation. So if you have two finite languages, assume that L1 comma L2 both are finite languages. In that case, what will be L1 dot L2? L1 dot L2 will also be a finite language, because if you have L1 which is finite, this is also finite. If you take their concatenation, then what will happen? You will again get a finite language. So we can say that set of finite languages is closed under concatenation operation. What it means? It means that concatenation of two finite languages is always a finite language. So that is the meaning of this closure property under concatenation. Now let's see some other operations. For example, you can see set difference. So you can very easily see the set difference. If you have a finite language minus another finite language, so this is a finite language, this is a finite language. Now finite minus finite, that is also finite. Okay, the result will also be a finite language. So we can say that set of finite languages is closed under set difference operation. So all these operations we have seen. Under all these operations, our set of finite languages is closed. Some other operations we can see, for example, reversal. Now reversal is also a very easy operation. If you have a language L, let's assume this L is finite language. Now what will be L reverse? L reverse will also be a finite language. For example, consider L, and L is, let's assume L is this is your L. Now what will be L reverse? L reverse will be this. You can see that language, if L is finite, then L reverse is also finite. So we can say that set of finite languages is closed under reversal operation. Some more operations that we can see. Let's see some operations under which set of finite languages is not closed. So for example, consider this complementation. Consider complementation operation. Okay, now assume that our alphabet is A comma B. So this is our alphabet. Now assume what is your language. Consider this language A comma, for example, you can consider this language A comma B. You can consider this very simple language A comma B. Now what is L complement? L complement, we know L complement means sigma star minus L. And what this L complement will be? Basically from sigma star we only want to remove these two strings. Okay, so what you will get, basically you will get all the strings except A comma B. You can see that this L complement, this is an infinite set. This is infinite. In this L complement you have all the strings over this alphabet except these two strings. So this is an infinite language. So you can see that we have a finite language. This L is a finite language. Okay, so this is our set of finite languages. From this set we have taken this L, which is a finite language. Now when we apply this complementation operation, this result does not belong to this set, because you can see this result is not finite. So we can say that set of finite languages is not closed under complementation operation. Okay, because complementation of a finite language can be infinite. So that is why you can say that this under this operation, complementation operation, our set of finite languages is not closed. Okay, you can take another example. For example, consider this L2. Which is phi, means empty language. Okay, you can see that this L2 is a finite language. Now consider this L2 complement. What is this L2 complement? L2 complement will be sigma star, and this sigma star is infinite. So you can see that the complement of a finite language is not finite. So we can say that finite languages are not closed under complementation operation. Okay, now let's see another operation. For example, Kleene star operation. Consider this Kleene star operation. If you have a language L, consider this language which is your A comma B. Now consider this language L. This is a language in which you have two strings A comma B. Now if I take L star, then what it will be? It will be A comma B whole star, and this is basically your sigma star, means this is your set of all strings. This is your set of all strings over 0 comma 1. Over A comma B. So you can see that this L is finite, this language L is finite, but when we apply this operation, Kleene star operation, then the result is not finite, the result is infinite, this L star is infinite. So I can say that set of finite languages is not closed under Kleene star operation. Okay, remember, closure property means this: you have set of finite languages, you take a finite language, L is finite language, you apply this operation, but this result does not belong to this set of finite languages. So hence we can say set of finite languages is not closed under Kleene star operation. So this is the simple idea. Now let's see two more operations for understanding. One is homomorphism, okay, homomorphism, and another is inverse homomorphism. So you can pause the video and you can try to think whether set of finite languages is closed under homomorphism or inverse homomorphism or not. Okay, so you can try to think about it. Let me tell you, the set of finite languages is closed under homomorphism, but it is not closed under inverse homomorphism. Let's see why. Because see, if you have a language L, let's assume this language L is over alphabet sigma is a comma b, and this language L is some finite language. Okay, some strings could be there, for example a b, a b b, b a b a. So this is your language L. Now assume you have a homomorphism. Consider this homomorphism: HA is epsilon and HB is also epsilon. Now consider this homomorphism. Okay, so in this homomorphism, what we are doing, the HA, homomorphism of A, that is epsilon, and homomorphism of B is epsilon. So what will be homomorphism of language L? That will be simply homomorphism of A is epsilon epsilon. So basically this will be epsilon comma epsilon comma epsilon. I can say that this is your homomorphism of L. You can notice one thing, that this L is finite and this HL, this is also finite. But this is just one example, but actually it is not hard to see that when you apply this homomorphism, then what will happen? Just focus here. Assume that you have a language, and in this language assume you have some strings, some w1, w2, w3, and some strings you have. Let's assume you have some w10, some 10 strings you have. Now you have some homomorphism. Assume that some homomorphism, that HA is something and HB is something. So this is your homomorphism. One thing you can notice, that when you apply homomorphism of L, then what will happen? Then you will get homomorphism of W1, homomorphism of W2, and so on, homomorphism of W10. So you can see that this also will be a string, this also will be a string, this also will be a string. So at most 10 strings you can get in this homomorphism of L. At most 10 strings. Some strings may collapse. For example, here also you can see in this language there are 3 strings, but when we apply this homomorphism, then we only get 1 string. So that is the idea. You can see that at most 10 strings you will get in this homomorphism of L. So I can say that homomorphism of L, this is finite. So hence you can say, if you have a finite language and you apply homomorphism, then also you will get finite language. So set of finite languages is closed under homomorphism operation. Now what about inverse homomorphism? The same example you can take, and this same example will tell you that set of finite languages is not closed under inverse homomorphism operation. Consider this language. Now consider this language L and consider this inverse homomorphism. Inverse homomorphism means H inverse of epsilon is basically A and H inverse of epsilon is B. This is your inverse homomorphism, because our original homomorphism was HA is epsilon, HB is epsilon. So this was our homomorphism. So this is your inverse homomorphism. I can say that H inverse of epsilon is A, H inverse of epsilon is B. Okay. Now from this you can see that if I have this language L, now what is the inverse homomorphism? Let's see, H inverse of L. So what will be the inverse homomorphism? Inverse homomorphism will be basically here set of all strings. You can see sigma star. Why sigma star? Because you can see what I can do. I can write this L like this. I can write like epsilon. So this epsilon, or I can write like epsilon dot epsilon. epsilon dot epsilon dot epsilon, I can write like this. Now if you have this epsilon, then this either, from this epsilon either I can get H inverse of epsilon is A also, H inverse of epsilon is B also. And remember, H inverse of epsilon is nothing but H inverse of epsilon dot epsilon, which again is H inverse of epsilon dot H inverse of epsilon. So you can see I can make AA, I can make AB, I can make BA, I can make BB. Similarly, I can do H inverse of epsilon is equal to H inverse epsilon dot epsilon dot epsilon. So I can make any 3 length string. Similarly, I can make any 4 length string, and so on. So I can say that if you have a language L, and this language L is finite language, and now this inverse homomorphism is sigma star, which is infinite. So I can say that set of finite languages is not closed under inverse homomorphism operation, because if you have a finite language and you apply the inverse homomorphism, then the result may not be finite. Okay, the result may not be finite. So that's why you can see set of finite languages is not closed under inverse homomorphism. So many closure properties we have seen for these finite languages, and the two important things that you need to remember, that what is a finite language, what is a finite set, this can be defined in many different ways. Many different definitions could be there. So in exam they may not tell you that language is finite. What they will do, they will say that you have a language and that language satisfies this property. Means for this language there exists a natural number such that every string has length less than equal to k. In that case you need to recognize, you need to observe that this language L is basically finite language. Okay. So the class of finite languages is closed under union, is closed under intersection, is closed under concatenation, but this set of finite languages is not closed under Kleene star, is not closed under complementation. Also, set of finite languages is closed under set difference operation, homomorphism operation, and set of finite languages is not closed under inverse homomorphism operation. Okay.